Alright, let's do some parallels. I've got we're going to make it a 12 volt source here. And I've got 1K, 1K, and 1K resistors. Now when I hook these up, I've got to make sure I connect the dots, because if I just go straight across, I'm not really connecting those first two. So I've got to connect the first, then the second, then the third. And I'm going to put an ammeter in here, so I'm going to go ahead and connect this to that, this to that. And then we're going to draw in a ammeter to get total current here. There we are. So 36 milliamps, and if we do the math here, let me bring up the calculator so you can see. We got a 1K in parallel with a 1K in parallel with a 1K, so we're going to use the reciprocal formula. So we're going to say 1 reciprocal plus 1. Let me restart that. 1 reciprocal plus 1 reciprocal plus 1 reciprocal equals 3. And we knew that because reciprocal of 1 is 1. And then we're going to reciprocate that. 0.333 is our total resistance. So if we divide 12 by 0.333, 12 volts divided by 0.333 ohms, or 333K, we're going to come up with 36 milliamps. So there you go. I mean, not 333K, either 333 ohms or 0.333K is what I meant to say. And so these are the equivalent. Remember, it'll always be less than the lowest, so 0.333K or 333 ohms is certainly less. So that's where we're getting our 33 milliamps. Now, unlike series, where when we add more resistors, current goes down because we're increasing resistance. As we add resistance here, current's going to go up because we're decreasing resistance. So I'm going to prove that by drawing in another resistor out here. Gotta add our wires. And there we go, current goes up because our overall resistance is lower. Because if we reciprocate 1 4 times, we come up with 4. And then the reciprocal of 4, if we do that on our handy-dandy calculator, which is right. I thought I pinned it to my taskbar, but that was my home computer that I did that to, so let me do it here. That way we don't have to pull it up every time. Alright, so basically I would have said 1 reciprocal plus 1 reciprocal plus 1 reciprocal plus 1 reciprocal, but reciprocal 1 is 1. Do that 4 times and you get 4. Reciprocate that and you get 0.25. Divide 12 divided by 0.25 and you get 48 milliamps, or 12 divided by 250 would give us the amp version, but this is in milliamps because we did it in the K version. So we've got 48 milliamps current flowing through each of these, and you see that this leg and that leg get total current. Current splits here, and because they're the same value, current is going to split evenly. And I'm going to show you that just by disconnecting. Whoops, I drew a line. Let me undo. Let me disconnect this first one. Of course, current's going to go up for just a moment. Actually, it's going to break it. So we're going to say draw, add components, and output some labels, ammeter. So we'll go there. And I missed it. So I got to slide it back a little bit. There we go. I got to redraw my path to here. There we go. So there's 12 milliamps going through this one. There's 12 here, 12 here, and 12 here. So let's prove that. So I'm going to escape. I'm going to come in here and I'm going to put an ammeter. Whoops. It's just going to be a pain. There we go. So we'll throw in an ammeter. Bring these guys back down where they belong. And we're going to say draw. And we're going to add an ammeter for each of those. And we've got to reconnect our circuit. And there we go. 12 milliamps through that one, 12, 12, 12, 48 milliamps total. But what if these were different values? Let's make that happen. So I'm going to edit each one of these. I'm going to do 2K. Edit this guy. Do 3K. And just to maintain some level of consistency, we'll make this one a 4K. Not that it really has to be. It could be whatever it wants to be. We know our overall resistance should be less than 1K. It should be less than our lowest one. So let's use that reciprocal formula again. 1 reciprocal plus 2 reciprocal plus 3 reciprocal plus 4 reciprocal equals, and then reciprocate that, 0.48. So that is 0.48 K or 480 ohms. So we'll keep it in K so we can get this milliamps. So we'll divide 12 divided by 0.48 K equals 25 milliamps. So there we go. So Ohm's law holds true, and look at the differences in the current. 12 milliamps through this guy, 6 milliamps through here, 4 and 3, and they add up. 12 plus 6 is 18, plus 4 is 22, plus 3 is 25. So it all adds up. Now, if you're troubleshooting this and all of a sudden current goes higher, one of these guys had to have changed value or been the wrong value inserted. So if I were to come here and I'm supposed to put a 4K, but whoops, I pull out of the wrong bin and I put a 5K, current, excuse me, that's going to go down. I meant the other way. So there you go. I'm thinking in terms of series. So we just reduced our total, increased our total resistance by a little bit, so current went down. So let's try that again. Let's re-talk about it. So let me do an undo. Alright, so we're at 25 milliamps. So let's see what happens if this guy goes to a 3K. And I'll talk about it after the fact. Well, we increase, and that's because our overall resistance dropped, and so therefore our overall current increased. Remember, our overall resistance a while ago was 0.48K. Let's see what it is now. So let's do 1 reciprocal plus 2 reciprocal plus 3 reciprocal plus 3 reciprocal equals, reciprocate that, and I think I hit the wrong button. Let me try that again. 1 reciprocal plus 2 reciprocal plus 3 reciprocal plus 3 again reciprocal equals, and reciprocate that, 0.46. So our resistance went from 0.46K or 461 ohms. So if we divide that into 12, 12 divided by 0.461, then we increase current. So resistance dropped and current increased. But if we go the other way, if we go to 5K, current's going to decrease this time around. And sure enough, it did. And we'll run those numbers just so you can see as well. We're going to reciprocate 1 reciprocal plus 2 reciprocal plus 3 reciprocal plus 5 reciprocal equals, and reciprocate that, 0.49 instead of 480, 0.491 instead of 0.48 something. So we're going to divide 12 by 0.492. 12 divided by 0.492, and that'll give us 24.4 milliamps, and that's what we're seeing. So that's one thing that could happen in a parallel, is a value change. Now what happens if we short one of these resistors? Let's see. So I'm just going to draw a straight line there, and this is where it gets a little unique. And notice my simulation stopped, and voltage source loop with no resistance, so it's not giving us true values. It's letting us know there's an error. what literally just happened is I shorted every resistor in here, and even though this thing's running, it's in a weird state. I'm going to leave it here because current takes the path of least resistance, and so current's going to be running along. It's going to, oh, there's some resistance there, there's some there, there's some there. Hey, look at here. So there's going to be no current flowing through these three, and basically we're going to short our source, which in the real world would either burn up wire, burn up source, or something. That smoke's going to happen, or we're going to trip an overcurrent protected device. So that's what can happen when we short one of the resistors. Now, what happens if one of these resistors open? Well, let's see. Let's pick the 2K. So I'm just going to cut him. Well, notice we still have current flow, but it's a lot less. And if you think about that, this is just like plugging stuff up in your house. If I plug something up, I'm going to have drawing some current with that one. If I plug something else up, I'm going to have a little more current. If I plug something else up, I'm going to have a little more current. If I plug something here, I'm going to have a little more current. But if I unplug any of those, I'm going to drop current some. And so there's still a path through here, we're not shorted. There's still a path through here, it's not shorted. There's still a path through here, we're not shorted. But there's not a path through here. So we lose that load, and it doesn't matter where that breaks, or if we just eliminate it completely, it's going to lower our current value by some amount, and it's going to be proportional to that particular resistor. So now we've just got a parallel circuit with a 1, 3, and a 5K, and we can run those numbers just to see. So 1 reciprocal plus 3 reciprocal plus 5 reciprocal equals, reciprocate that, 0.652. So there we go, our resistance is higher. And if we divide 12 divided by 0.652, we get 18.4 milliamps. So there you go. So that's what can happen in a parallel. This is how Falstad can help you see some of these things. So I hope that makes sense to you. And this is some of the mindset you need to have when you're troubleshooting.